Hello, and thank you, Igor Pak. Thank you, Greta Panova. I am Tadashi Akagi, Javier Akagi, and this work is a joint work with many peoples, where Manjil and Marcos is here today with us. This I will talk about the computational complexity of the L-Tromino tiling problem. And the tiling problem is like a tessellation, but instead of filling an entire plane, it will fill just a very delimited portion of using some geometric shapes called tiles. Okay. I will introduce you about polynomials and the main problem, and we will see three variations of this tiling problem and its complexity. Okay, polyomino is a planar figure made from one or more equal sized squares, each joined together along an edge. So we are considered two cells adjacent if if they are adjacent horizontally and vertically, and diagonally we are not considered diagonal. So here we have three polyominoes, which one of them is L-tromino. The green one we call L-tromino. Okay. Our main problem is the L-tromino tiling problem. The problem have two elements: the tile set and the region. The tile set is a list of polyominoes that are allowed and be used to cover a region. The tiles can be used as many as you wish, and in this particular problem of L-tromino tiling, we have 4 orientation of L-trominoes. The region is another polyomino, usually more bigger, and it defines the area that should be covered. And the goal is cover every cell of the region such without sorry. The goal is to cover every cell of the region, placing L-trominoes without overflowing the perimeter of the region and without overlapping tiles each other. For example, this is a region R, and this is a L-tromino tiling of the region. It is known that the decision problem of the existence of the L-tromino tiling, it is NP-complete. Moore and Robson already proved in 2000 that with a reduction from cubic planar monotone 1 in 3 SAT to L-tromino. And later, Horiyama et al. In 2012 also proved with a more simpler reduction from 1 in 3 SAT. Okay. And now we'll study a tiling problem in a simple region called an AZTEC rectangles. An AZTEC diamond is a polyomino that is obtained by considering only sorry. The AZTEC diamond is the union of all cells inside of the contour defined by this formula. This formula is just a square rotated 45 degrees with the center of the square in the origin. And these are the AZTEC diamonds, and the AZTEC rectangle are just a generalization of the AZTEC diamonds. This is an L-Tromino, and it covers 3 cells. Therefore, every L-Tromino tiling will cover always a multiple of 3 cells. This is a very basic necessary condition for the existence of L-Tromino tiling. If we want to tile an AZTEC rectangles of order AB, we can use this formula that gives the number of cells of an AZTEC rectangle. If the number of cells of the AZTEC rectangle is a multiple of 3 when A and B have the form 3k or 3k minus 1. And we can also show that we can always tile an AZTEC rectangle of a multiple of 3 cells with the following algorithm. The problem of the problem of tiling an AZTEC rectangle can be solved using these patterns. The pattern 1 is this and this. The pattern 2 is this. These patterns are used depending of the value of the A and B. When the AZTEC rectangles is gets more thinner, we use these patterns to keep reducing the size of the AZTEC rectangles. And the base case are the AZTEC diamonds of order 2 and order 3. The problem of tiling an AZTEC rectangle can be solved recursively. And here we can see the tiling. The defect cell is sorry. Now we add a restriction to the problem called defect cell. A defect cell is a special cell where we cannot place an L-Tromino on top of the defect cell. If we have just only one defect cell, the number of cells of the AZTEC rectangle, it will reduce by 1. Therefore, we want that the order of the AZTEC rectangle be 3k minus 2 to have a to have a multiple of 3 number of cells. If we have defect cell, first we locate the defect cell and we place a fringe where it is the defect cells. And we can tile the fringe trivially from outside toward the inside. Then we place stairs from the fringe to the outside to get the tiling of the AZTEC rectangle with a single defect. When the number of the defect is unbounded, the problem is it becomes NP-complete. This is because we can construct an arbitrary region R prime in a sufficiently large AZTEC rectangle like this. We just set as the defect cell all the cells outside of the region R prime. Okay. I'm sorry. I'm very. Okay. Now we add a rotational restriction to the L-tromino tiling problem, where we only allow 180 degrees of rotation of the by 180 degrees. So the tile set now we can consider only 2 orientation. It could be the right oriented or left oriented. And we will analyze with no loss of generality the right oriented 180 terminals. This restriction is interesting because there is a relation to another very different tiling problem called triangular trihex tiling. And triangular trihex is this shape, the hexagonal shape we see here. And there is one-to-one correspondence between the 180 terminal tiles and the triangular trihex tiling. So these problems are equivalent. And okay, so there is a lot of this 180 rotation restriction gives to the problem some nice properties and symmetries, like like in this relation to another tiling, and it appears some properties like color argument. So we hope that this problem could be solved in polynomial time, but we couldn't find a polynomial algorithm. Therefore, we have introduced a new operation called tetrasection. Cell tetrasection is a division of a single cell into a 4 equal side cell. And a tetrasected polyomino is polyomino that is obtained tetrasecting each cell. So, for example, if we have here an I-tromino, and then tetrasecting the I-tromino will be something like this. And note that if we tetrasect an I-tromino, this can be tiled with 180 trominos. So if we have an I-tromino of a region R, we can find 180 tromino tiling for the tetrasected region by replacing each I-tromino by 400 tromino. Okay. But we don't know if the covert statement is true or false. That is, if we have a tetrasected region, if we know that 180, if a tetrasected region can be tiled with 180 tromino, then we don't know if it can be tiled with an I-tromino in the untetrasected region. This statement is important because it will give immediate proof of the NP-completeness of the 180 tromino tiling. Okay, so we took the Horiyama reduction which proves the NP-completeness of I-tromino. It gives the reduction from 1 in 3 SAT to I-tromino. And in this reduction, use these 6 gadgets. We have realized that if we tetrasect the gadget, the I-tromino tiling can be simulated with 180 tromino tiling. So we can use these tetrasected gadgets to simulate the I-trominoes and the tilability of the I-tromino. And therefore, this gives NP-completeness. This gives a reduction from 1 in 3 SAT to 180 tromino tiling. The 180 tromino tiling can also be reduced to the maximum independence set problem. And this reduction can be done as follows. We can take each cell of the region and into a point, and we add horizontal, vertical, and diagonal edges in such a way that each triangle on this figure corresponds to a 180 tromino on the region R. Then we transform again this figure and taking a triangle, each triangle transforming into a vertex. And we connect 2 vertices, and if these triangles have an edge or an vertex in common. And the obtained graph is the intersection graph. The intersection graph will gives if we get a vertex in the intersection graph is 180 tromino in the region, and if there is an edge between two vertices, and the corresponding 180 tromino will be overlapping each other. So if we find a maximum independent set of this intersection graph, then we can find a 180 tromino tiling of the region. And so if the number of independent set of the intersection graph is equal to the numbers of cells of the region R divided by 3, then the region will have a 180 tromino tiling. If the intersection graph is a cloud-free graph, then it is known that cloud-free graph can be computed the maximum independent set in a polynomial time. A cloud is this graph. So we have identified 5 polynomials that generate the smallest. We have these 5 polynomials are the smallest regions, such that its intersection graph contains a cloud as an induced graph. And we call these polynomials as forbidden polynomials. If a region have a forbidden polynomial, then it can be if a region doesn't contain a forbidden polynomial, then 180 tromino tiling can be computed in polynomial time. Finally, we have the tetrasection, a tiling algorithm for a tetrasected region. Tetrasected, we have find that a tetrasected region can be always tiled with an L-tromino if and only if the number of cells of the region is a multiple of 3. And furthermore, we found an N-log-N algorithm that computes the L-tromino tiling of the tetrasected region. We divide this algorithm in 2 cases. The special case is when the dual graph of the region is a tree, and then we will analyze the general case. The dual graph of a region is a graph that can be obtained transforming each cell of the region into a vertex, and we connect the vertices by the adjacency of the cells. So we will analyze when this dual graph is a tree. Let's suppose the region have a multiple of 3 cells, we define a tag of a cells as the number of as the size of the spanning subregion in modulo 3. For example, here we have as in app we have the size 2, so we place these two. Here we have from the right we have 5 cells, and in modulo 3 it's 2. And the sum of the tags is always will be 2 in modulo 3 because there is one less. We are counting. We are not counting this cell. We have identified 7 kinds of tag cells, and the algorithm of finding the tiling of the tetrasected region is by running a depth first search traversal into a dual graph and compute the tag of each cell. Then we replace the tagged cell with the following tiling patterns. So here we have the tag cell with only 2. So we use these tiling patterns, and we place these tiling patterns considering the orientation of the tag. By this simple substitution, it will emerge an L-tromino tiling of the region. To attack the general case, we have to consider the dual graph with a cycle. If the dual graph has a cycle, we have to partition the region into 2 or more subregions such that the number of cells of the each subregion is a multiple of 3, and the dual graph of the each subregion is at 3. So we can apply like this. So we can apply the previous algorithm into each subregion. And the algorithm for partition the region is first computing the dual graph and compute any spanning tree of the dual graph. Then we take any edge from the dual graph and we insert it into the spanning tree. So it closes a cycle. Then we take arbitrary 4 edges of the cycle and try all combination of the cutting the edges and to find we select 4 different edges and we try the 4 combination of 2 to partition the graph into a 2 subregion with each of them having a number of 3 number of cells. and this is always possible. So, and we apply this procedure again to each subregion, and we stop the recursion when each region is a spanning tree. It's just a tree. And this is how to partition the region with a cycle. Okay, thank you.